comes down to AI. That's why the second part of the talk will be looking a bit into the future and current work that we're doing on the topic of democratizing generative AI. The first part should be more generally accessible to just lay this stage, and I hope with that I can do best to serve both sides as good as I can. Democratization of generative AI. Why now? Why with this pace, and where is this going? Now, I believe the reason why generative AI turns out to be so powerful and so rapidly going out in all of society is because it's become an afterburner for things that we've been doing all along. An afterburner for the personal computer. The personal computer, which is super versatile in its abilities, that we've all cherished for a lot of tasks. But let's face it, if you want the personal computer to do something that it's not been programmed for, it becomes hard. Computer scientists, by training, should be able to program the machine, but even for them, it's an error-prone task to teach the computer in its very own language, a programming language, to do a certain thing. It's costly with that, it's error-prone, and only very few have this ability. Generative AI is changing all of that, because now we can advise the computer to do new things in our own language. The machine finally understands what we want from it in our very own language. So in a sense, the personal computer, the PC, becomes now truly personal. It understands what users want, what they need, what they may be lacking for, and all that in their very own language, in our very own fuzzy languages. So in a way, you could say that although it's been called a personal computer, the only personal thing, the real personal thing about the PC was that you personally paid for it and you personally owned it. But all the applications that you had there were really from the rack, the content that you consumed. That was pretty much the same. You had a few knots which allowed you to personalize it by set the colors a little bit different and maybe change the language of the machine, but apart from that, that's been basically it. And now the machine understands what you really need and sort of communicates with you on the very language and level that you're standing at. Now, when we're talking about generative AI, there's one misunderstanding that I want to sort of get rid of right at the beginning. Generative AI, you think about things like stable diffusion systems, where you can, in natural language, describe what you want to see in an image, hit a button, and then a sec later or so comes out an image like this one. But my team and others are working on that, not just for the purpose of building image or video generators, but in so doing, the machine learns something about our world, learns to understand objects and what words means and so on. And this you can then utilize for entirely different tasks to reason about images. We're collaborating together with neuroscientists. You want to understand neurodegenerative disease. If you have cancerous tissue, you want to just visually search for something similar. Or if you're in a shopping business and you want to find a similar product. All of these things are related to image understanding, and the machine that can render images, you can turn that process around and have it also understand images. A computer that understands us in our fuzzy natural language and understands really what we know and what we don't know evidently becomes a much more effective tool. A more effective tool to boost our productivity, making us work faster, as this science study here showed, better in terms of our outcomes, and interestingly, taking teams which are a little bit inferior in their skills and really ramping them up, with them reducing certain amounts of inequalities. So as it stands, we're looking at generative AI as a technology which I would really call an enabling technology. Enabling technologies are technologies that you don't just build for themselves, but because they become enablers for future technological progress. You haven't invented electricity or the PC just because electricity was beautiful in its own right. No, but because of the millions of other technologies that you could only sort of put together once you have access to electricity. And so it goes that generative AI is such a power enabling technology which is starting to enable thousands upon thousands of other technologies building upon that. And with that, I think this study here from McKinsey, which estimated that the global added value by means of generative AI will go in the direction of annually of the annual GDP of Germany, is probably making sense in that particular reason, for these particular reasons. But let's now go a little bit deeper. AI is said to have been there for a lot of years. Generative AI has been also there for quite some time. What's different this time around? What separates this from the hypes that we may have had in the past? Why is there, as I believe, more substance for betting on this technology this time around? Well, generative AI has always kind of faced a dilemma. On the one hand, you want to have models that have great quality. I mean, who wouldn't want to have a model that outputs great quality in whatever it's outputting, text, images, whatever that is. On the other hand, however, you want to be able to cover pretty much all the world when you really understanding the world, not just like narrow niches, be it only the training data. No, you want to learn from finite training data to essentially be speaking about the entire world. Think about the training data as being tiny islands in the Pacific, your individual data points. But you want what you really want from a true intelligence is kind of to extrapolate away from there and fill in the water in between with new land, have their new data essentially be made up in a reasonable manner. And bringing these two things together, great sample quality and at the other end really being able to speak about everything, great data coverage, is a challenge. Now, diffusion models, transformer architectures, powerful likelihood models that have been somewhat recently invented fill this gap in between. They allow us now to get both at the same time, a great quality and a great coverage. The reasons for that are a bit more technical. For those in the room in that particular field, we finally get rid of this partition function that you know from physics, this normalization that you always need when you talk about probability distributions, and which is so complicated because to get that you essentially need to integrate over all the world, which is never possible. But these models suffer from, especially here diffusion models, from these long Markov chains. What do I mean with that? Well, to train a diffusion model, which is at the core of stable diffusion, which to a certain part I will be introducing here, to train such a diffusion model, what are you doing? Well, you're taking training images, like this cute little dog there, and you add noise to this dog, just a tiny bit, so that you and I would not notice the difference. But you repeat this process of adding a tiny bit of noise hundreds or thousands of times, until at the end, the result looks like you plucked the cable from your TV set. Pure noise. Why in the world would I actually remove this dog there from the image and turn it into pure noise? Well, I do this because then I can take an AI and turn this process around. Train the AI essentially by taking a noisy image and an image which is a tiny bit less noisy. These I have available. And then say, hey, AI, get rid of this tiny bit of noise. I guess we can all imagine that that should be kind of possible. There's such an autoencoder architecture here, for instance. And the beauty, however, or the magic happens when you repeat this denoising process now hundreds or thousands of times, because then you're starting with pure noise and eventually end up, well, not exactly with this dog, but which is with something which is qualitatively somewhat similar to that. And with that, you get kind of something which is kind of close to the holy grail of computer vision. We now finally get a semantic hierarchy in representation. So far, the only thing that we could get were images which get smaller and smaller, more blurred and more blurred. But now finally we get images which are all the same resolution, all the same crispness. The only difference is, if you're going from left to right in this hierarchy, that they're having less and less of the semantic details. And with that, you get levels of abstraction and teach the machine to understand images based on different levels of abstraction. But, as always, there's a kind of dark side to that, because the strength of these strong likelihood models is at the same time also becoming sort of their weakness. These models now tend to home in on every bit and detail of the probability distribution over the world. Try to memorize pretty much everything that is there. If you have this dog from beforehand, they try to memorize each and every pixel there. Something that we wouldn't do. You just memorize like, hey, this dog was grayish, but not where each individual hair was pointing. And with that, you get a problem which is depicted here in this rate distortion curve, where on the horizontal axis you see the data rate, how many bits you actually need to describe something. On the vertical axis you see the distortion that entails. And evidently you want to have as little distortion as possible, be at the bottom end, but you also want to utilize as little bits as possible. Now the problem is that these models typically spend most of their bits actually for details that you and I would not care about. Yeah? Details between the bottom right faces here, which I don't even notice what that is, differences in individual pixels. And comparably fewer bits on the things that actually matter to me, semantic details between like length of hair, whether the person is wearing glasses or not, probably different gender here, and so on. Yeah, and I actually want to learn the green part. So how do I get more information from this green part? Now the classical answer has been to just make the models larger, because with that your rate distortion curve moves to the top right. You get more bits in there, and with that you also happen to get more bits in the green part. That's kind of wasteful, right? Because most of the purple area will also increase, and will increase much more rapidly than the green area. And that is kind of where we were going as a field. Models were getting larger, horizontal axis here being time. Models were getting larger at a staggering rate, like 4x per year or something like that. Now you may say like, yeah, but computers are also getting cheaper, and especially with GPU computing, right? Well, not so. We've now increased model sizes by a factor of 15,000 over the last 5 years, and that is considerably faster than even the GPUs have been growing in the same time. Roughly in order of magnitude are our models getting faster than the GPUs are. And the result, when something like that happens, supply and demand being totally out of proportion, things are getting more expensive. And that's pretty much the rate that you see here that's projected currently for model development and the cost that it takes to develop frontier models. Just to put this in numbers, if you look at something like GPT-4, we're talking about tens of millions of dollars, somewhere 50 to 100 million of dollars for training such a model. And just imagine, like, you screw something up, you need to restart the training. That's going to be a costly error if you figure that out a little bit later. If this trend continues, by, let's say, in 3-ish years, $1 billion for a model, and you better make sure that you have a clear trajectory towards revenue, right? If you have upfront costs of $1 billion to invest in that case. Ever more training data needed for these models. Question is really where we will get more uncorrelated training data if you've already scanned the entire internet. And last but not least, fewer and fewer players having actually the resources that it needs to do such training. And there, that's how I open my talk, I see a critical issue. If we really consider that to be the critical technology on which of most of our economic development, society and so on will build, having a monopoly there of some foreign companies might be tricky, let alone like where research is going. So what's the way out? I believe like there is a certain delusion in scaling. Not that scaling would not be effective, don't get me wrong there, it has truly helped, but if we bet all on scaling, that would be a bit of a tricky issue. It turns out that our brains have also not just like scaled as we moved into the information age. It turns out that we pretty much have the same cortical hardware, but at the same time we moved from the left there, sticks and stones, to operating very complicated machinery. Although we had finite resources, I would go one step even further and say, because we had limited and finite resources, we were able to develop intelligence. Because it turns out, the moment that you have finite resources, you need to start becoming clever and finding intelligent ways out, or you simply cease to exist. Yeah? And we see this in machine learning with these bottleneck architectures for those in the field, because you introduce some bottleneck through which information from the left and right needs to pass. We need to abstract something away, and that's the dawn of intelligence. That's what you demand from students, right? Other than that, they would just come up with all the books that they had for class, sit there in a test and just copy it there, and they would be done, right? But the moment that they need to funnel that and compress that together to then answer questions, that's where intelligence actually starts. And it turns out we've probably done a little bit too little of that in developing intelligence, artificial intelligence. So our goal in democratizing AI was taking artificial intelligence, which takes billions of training images, hundreds of terabytes of data, and so far consumed hardware, not just during training, but even during inference, which potentially costs like millions of dollars, compressing the models so that they fit on consumer hardware. For $300 these days, Stable Diffusion fits on your mobile phone. And that means that we need to compress something which were hundreds of terabytes of data down to something. Our goal was 10 gigabytes of memory. Yeah? Thousands upon thousand-fold compression. And that is exactly where true intelligence comes about, right? If you need to compress that much data to its essence, and that's also where you get democratization from. Because now this technology becomes accessible not just to the few big companies who have millions of dollars, but also to the lots and lots of research labs and smaller companies who now have smaller models being made more powerful. Quickly, how does that work? The idea here was that we have architectures which are very efficient and architectures which are very powerful. The diffusion models that I showed you, autoregressive transformer architectures that many of you have heard of, they're very expressive models. They're great in modeling long-range dependencies, guaranteeing that it's not snowing in the left-hand side of the scene and you have a beautiful beach day on the right-hand side of the image. Something that we've been struggling as a field for a long time. Now finally we have this complexity to make sure that we establish these correspondences there, but they're expensive. They are much too expensive for the local details there. On the other end, we have the good old convolutional neural networks, which have now been around for several years, depending on the stage, like 25 years or more. And they were at the start of the current revolution in deep learning in 2012. They are great for modeling the local interactions. And they can do so very effectively because of their tiny receptor fields, but they're not great for modeling long-range interactions. So our goal was to combine the strength of both architectures and essentially take a generative model here for rendering images or video or 3D, but not do that directly. Rather than that, learn first a language which is much more effective in doing the generation. Now, if we were to render this dog, we would probably memorize, yeah, grayish dog there, kind of short hair, but you would definitely not remember where each individual hair of the dog is pointing. If I were to render that, I would just say the artist like, hey, do it. Yeah, I don't care like where the hair is pointing, just do it. And same thing here. This level of abstraction, that's a convolutional network there at the top, takes care of the local details, the texture, and the generative model at the bottom then can start to see the forest for the trees again. It can now start to establish long-range interactions in that scene, really start reasoning about the scene and not being overwhelmed with all of these local details because it operates in this much more effective language. And then you can condition this model also with site information like text and guide the model in rendering the image and say like, yeah, I want to see an image of a cute dog, and it's doing so. So the result of that was the model that you may know as Stable Diffusion. We just type in text, a sunset over a mountain range, oil on canvas, or here's a vector image, it comes out. It's a model where you can throw in an image and say like, get rid of this tree here and imagine what could have been behind this tree. You can do the CSI trick, yeah, take a small image and say like, make large and invent the pixels which were missing in between. Or you can take something which is probably more of like my artistic skill and turn it into something more beautiful at the bottom. Now, Stable Diffusion, then on top of that, enabled a lot of other applications. Applications like Meta built on our approach to generate their LMU model. It's integrated in Apple's core ML stack, so if you have Apple hardware, like Intel does this, Intel Inside, there's not a Stable Diffusion Inside sticker or something on there, but it's core part of their intelligence. It's there in 3D rendering tools and video rendering tools, and interestingly enough, also in these things for establishing correspondences, which are more like discriminative tasks, not so much like generative rendering tasks. Now with that, I want to transition to the present and the future. In training generative models like Stable Diffusion, you spend quite a bit of energy, time, and money to get these models together. Now once you have this box there, this generative model, which gives you an understanding of the world, allows you to sample, to render images from the world. How can we use these models for entirely different tasks? And how can we do so more effectively that we don't need to start again? And I'm going to show you some examples of that. In recent work, we've been exploring, for instance, how we can utilize these models to reason about the three-dimensional structure of the world, the depth of images, which you see depicted here. Reason about like 3D renderings, although we've trained the model just on 2D images. We've been taking this model to establish relationships between text and images and get both worlds together. And last year I will show an example for taking these models to then establish correspondences, semantic correspondences between images and do registration. Now, the first I want to show is some recent work of ours which goes in the direction of adapter approaches. Adapter approaches are very powerful because now you can take a model like Stable Diffusion, but it also works with other models, and keep the model fixed, but adjust it to your needs during inference. So let's say I want here a high quality detailed image of, in that case, this young boy there. And I want to fix the posture now and change it, not to be the boy anymore, but image of Lincoln's statue or whatever, but keep the body posture fixed. Then you want this adapter on the input accept additional information than just the text, a body posture. Now, it turns out there's many different ways that you could actually want to fine-tune or nudge such a model, not just by means of body posture, but you could also give it a depth map, or you could be interested in getting just the style of the image on the input side. And it turns out there's not one adapter to rule all of these problems. It turns out there's an invisible divide between these problems. There are approaches at the bottom which are more like localization problems. Hey, I want to keep the body posture fixed. And there are problems which are more like overall context. I want to keep the style of the image fixed. And although for us, this is all like, hey, I want to guide an existing model and have it do something else, it turns out here, for the computer, these are two entirely different problems which need to be solved by entirely different approaches. Now, if you ask me, a true intelligence, a visual intelligence should be able to solve all of these problems, but it turns out that wasn't possible so far. So how can we get beyond this invisible divide there? And build an approach which can do both, global style, local structure, do so very effectively. That's the size of the disk here, requiring few parameters, and with that, very few images, training images. Now for the experts in the room, what you typically have is a model like Stable Diffusion and a that box there, and we keep this frozen, and what you do is you build an encoder-decoder architecture there, typically much smaller than what you've seen in ControlNet, and you train this. But you need to train this bypass to your Stable Diffusion or generative model. You need to train it for each individual task, which is again making it costly and not very versatile. Now our goal was to keep this part fixed, and we've observed that in the latent space, in this intermediate space of this bypass, is a low-rank representation. That's why these things are called low-rank adapters, LoRa's. In this low-rank space, we essentially have an affine transformation, and we can simply just train the parameters of this representation by injecting two neural networks. One takes care of the local, the other takes care of the global details, and this thing is now becoming a conditional adapter, meaning I can on the fly, in a zero-shot manner, just change the input, the conditioning, and say like, hey, I want to get the depth map there of this deer, or more like the style of the toucan, and go for it. And you can just flip this as you wish, and you never have to retrain it again afterwards. And that allows you to then even interpolate between the different sources of input and create some weird creatures like this one here, and allows you to take different input here. You can run the same model, there's some depth maps, based on edge maps, human posture, whatever you want, and it works and understands all of these things together. Next up, what can we do once we've learned a generative model to register images? To say like, I have some tissue, for instance, I want to register that against similar looking tissue. If you're a medical doctor, if you're having posture there, human posture, and you want to find related postures of somebody, we have some study together with neuroscientists on neurodegenerative disease, which evidently lead to impairment of motor function, to relate that. Whatever it is, you have images, and you need to relate them. And for that, you need a representation of the semantic content in the image, to say this green box that I have there, this green circle on the left, or a blue circle, correspond to these here on the right-hand side. Usually models, diffusion models, have been used for that. Once we released stable diffusion, very quickly after, people use these diffusion features, diff features as they're called, for exactly that purpose. Yeah? So again, it's not just something Hollywood style for rendering images, but something stable diffusion now, which you utilize to understand images, to establish correspondences. The only problem with that is you have a free parameter. You have this noise level that I mentioned beforehand, and there's not one noise level which is going to solve all problems equally, as you see here. And secondly, as you're adjusting the noise level, you add noise to your image. Noise leads to the image details being blurred out, and in that case, your features deteriorating. So our goal is to have, for one, not a free parameter anymore, get the best out of all the different time scales that you had beforehand, and secondly, not needing to add noise or blur the image in the first place, to just get higher quality features. Now again, for the experts here, how is that working? At the top, you see stable diffusion. You take the image, you add noise, and you get somewhere in a later layer of this frozen network, you get the feature representation, noisy features, which is what people have used so far in our diffusion features out of stable diffusion, for instance, to establish correspondences. Now what we're doing is we're creating here a tiny copy of this network, adding a projection layer at the end, but the kicker is this model receives as input not the noised images, but the pure image, no noise being added there. And this model at the bottom can therefore deal with the pure image content, not some details being obfuscated by noise being added. And that's why we also called it clean diff, because now we get these clean features. How? By essentially taking this projection layer and minimizing the distance between the features that we have at the top and the bottom. And the model at the bottom also does not need the time scale because we don't add this noise to the images. So we get the best of both worlds. One, clean features, because we take clean images as input, and second, which you see there on the right, no time step needed. And with that, the model gets better in semantic matching, in estimating 3D depth of the scene, and in segmenting scenes, for instance. And if I have another 3 minutes, yeah, then I can show you the last part, because so far, most of the talk was all about what can you do once the model is trained, and how with stable diffusion can you make sure that you don't require like millions of dollars for the hardware, you can do it just on your mobile phone. With the later approaches, what you can do so that you don't need to retrain again, and you can more effectively recycle the models. Now, I'm going to show you some very recent work of ours, which we call track, for improving the training of the model architectures, which probably many of you have heard is the most costly part, the reason why big companies like Meta and so on have been buying hundreds of thousands of GPUs, which are worth like tens of billions of dollars. So we've been asking ourselves, how can we make even that part more effective? And it turns out that the driving force of all of the training have been transformer-based architectures. Transformer-based architectures which take an image, divide this in a bunch of patches, which you see here at the bottom. We call these then tokens, much like in your LLM, where the text is divided in tokens. Then noise is added on top of that, and you get a diffusion-based transformer architecture. Now, the complexity of that model, however, depends on the number of tokens, because it's adding quadratic relationships between tokens, and with that the complexity goes up quadratically as the number of tokens go up. Solution? Well, so far you just kick part of the tokens into the bin. And you just disregard them, fewer tokens, training faster, done. Of course, if you throw something away, you lose information. That's probably not the best way to go about it. That's why others suggested masking in that case, which means I take the tokens, throw them in the bin, but I introduce empty tokens sometime later, so they don't need to go through the entire architecture, less processing time, but they're still there, at least close to the end of the architecture. Problem with that, well, I said the diffusion process, the benefit is that I'm always doing just tiny steps, tiny bit of noise added, tiny bit of noise removed. In that case, you go from nothing, black image, to full image in one step or whatever. Not very good, right? And that's why we introduce here these token routing strategies. The idea here is you're not kicking the token in the bin, you just have the token skip a lot of processing in your architecture. Essentially add a bypass, and with that you bypass a lot of the processing, things get faster, but you're still introducing a somewhat noisy token at a later processing stage. You're not starting like in the masking approach with nothing, with zero, but already with a signal. And that, as you can imagine, simplifies then the denoising step and improves with that the signal that you're getting on the output side. The result, x-axis is training time, the horizontal axis is the quality in FID, so the lower, the better. You want to be ideally in the bottom left corner, and you see that green, our tread approach here, gives you more than order of magnitude improvement over the existing architectures. And what's important here to mention is you can put it on top of whatever architecture you want, just like stable diffusion. We've been experimenting here. A few days ago I was at New York University. They invented on top of our stable diffusion approach diffusion transformers, which you see here. You can put tread on top of that, or REPA, and see gains based on these architectures as well. Let me wrap up. In order to democratize generative AI, it's of crucial importance to boost the efficiency of generative architectures. Stable diffusion did so by inventing a new language, so to speak, a latent representation of images, and not doing all the generative processing in the detailed space of individual pixels, but in this much more compact representation of latents, and then have a convolution neural network kind of do the rest. So essentially advising the convolution on your network what to render, but the local details it takes care of. I then showed conditional low-rank adapters, which are efficient and very flexible model-agnostic architectures, which allow you to do a zero-shot transfer of an existing model to entirely new tasks without having to retrain. We looked at CleanDiff, which takes diffusion models, not for generating images, but for all the tasks where you're interested in discriminating between images, finding related matters, and it removed the noise from this process. And last up, we looked at token routing strategies. Token routing strategies to improve the training of these architectures by simply bypassing much of the processing. Just as a side note here, DeepSeek you heard of. DeepSeek uses, for instance, mixture of expert approaches, not the entire architecture anymore, but only parts. We've seen the dramatic improvements and what that did to the NVIDIA stock back in the day. This year does something similar in the direction of the generative models for images that were shown. So with that, let me thank you for your attention. I'm happy to answer any questions if you have.